Welcome back to the Math Fun Room. In this video we want to take a look at a introduction to series. Now in a prior video we would have talked about sequences, and a quick refresher here for a minute or two about a sequence. So we might have the list of numbers. Let's say we have 1 and then -1/2 and +1/4 and -1/8 and +1/16, and let's say so on and so forth, right? So in the prior video we talked about this sequence being basically a list of numbers. So with this list of numbers in particular, we could write what we call the nth general term, right? So for this nth general term, we could write this as, let's say, -1/2 to the n-1, and n goes from 1 to infinity. Right? So again, if n equals 1, I get -1/2 to the 0, and there's 1. If I get n equals 2, 2 minus 1, and the exponent is 1, so -1/2 to the 1 power is -1/2. When I plug in n equals 3 and the power, I get 3 minus 1, which is 2. -1/2 squared is 1/4, and so on and so forth. So here's the nth general term of my sequence. Now what we're introducing in this section is what we call a series. So in this series we're going to sum up the terms of a sequence. Now if I think of this particular example that we're looking at here, I have -1/2 to the n-1 as n goes from 1 to infinity. So instead of just listing the numbers, we're adding them together, right? So this is going to be 1 plus -1/2 plus 1/4 plus -1/8, and so on and so forth. So in the prior video, when we talked about sequences, we talked about what it meant for a sequence to converge. And in essence, we used the limit. And we said that the limit of the a sub n, right, so if I look back at my sequence here, if I said the limit as n goes to infinity, if that has a limit that exists, we wrote the limit of a sub n equals L. So if L is finite, if that limit exists, then we say the sequence converges. We're going to use the kind of same concept here for a series. So in other words, if I look down here at the sum of terms, if this sum of terms approaches a finite value, then we're going to say that the series converges. Otherwise, if this sum is not a finite value, then we're going to say the series diverges. Now, what's really interesting here as we look at an initial conversation is how can a sum that is infinite, how can I add infinitely many numbers together and get a sum that is a finite number? That's a great question, and that's what we're going to explore over the next 3 to 4 sections, and then eventually at the end of a chapter like this where we look at what we call a power series. All right, and let's go ahead and consider a different series here just to kind of lead us into the next couple examples that I want to discuss. So let's say we also have the series, let's say, get my digital pen to work here. So we're looking at the sum of 1 over n cubed. This is going to be a little easier to look at as we explore. Right, so this would be, 1 over 1 cubed plus 1 over 2 cubed plus 1 over 3 cubed, 1 over 4 cubed, so on and so forth. Right? So our question here is, does this series converge or diverge? So how we would typically approach this is we would convert this into what we call a sequence of partial sums. So if we look at the sequence of partial sums, in other words, if I look at the sum of the first term, that's just 1 over 1 cubed, which would be 1. It's kind of funny to say the sum of the first term because I don't really sum anything, I just list the first term. But this is the language that we use, the partial sum. So if I sum the first 2 terms, we could find what that number is, and I'll come back and do that in a second. We could find the sum of the first 3 terms, so I would look at 1 over 2 cubed, 1 over 3 cubed, and find what that number is, and again, I will come back and do that in a second. We look at the sum of the first 4 terms, right? What does that look like? Now I'm going to get a little efficient, and let me erase that for a second. So think about this for a moment. If we look back here, the third partial sum was really the sum of the first 2 terms plus the next term, right? So we could have written this as the sum of the first two terms plus the third term, a sub 3. So I could look at the sum of the first four terms as the sum of the first three terms plus the fourth term. So in this case, we'll have that number that we're going to write up here in just a second, plus the fourth term, 1 over 4 cubed, and so on and so forth. I could look at the sum of the first 5 terms. That's the sum of the first 4 terms plus the fifth term. So that's the sum of the first 4 terms plus 1 over 5 cubed. So I'm going to pause the video for a second and take out my calculator, and I'm going to get numbers for these partial sums. I will be right back. Alright, so I'm back. So here is the sum of the first 5 terms. Here's my sequence of partial sums from S1 to S5. Now when I look at these numbers, right, here's 9/8, well here's 1, and then 9/8, and then 251 over 216, and then 2035 over 728, and 256103 over 216000, and I used Wolfram Alpha to help me add those numbers and get exact values. So again, if we think of the sequence of partial sums, the first sum, the second sum, the sum of the first 3 terms, right, the fourth partial sum, the fifth partial sum, comma, comma, comma. So I would list all of these numbers out, and it's a little bit difficult for me to, the 1 is the first one. So 1 and then 9/8 and then 251 over 6. All right, so it is a little difficult to see really what the behavior of these numbers are in this, fraction exact value form. So what I want to do next is let's convert these to decimals so we can get a little better feel for how these terms are behaving. So if these terms are getting bigger and bigger and bigger and bigger and bigger, then my sequence is diverging. So if the sequence of partial sums diverges, when I get out to the infinite sum, it's diverging. Now this is really bad symbolism. This is not really mathematically correct, right? But I'm just saying this infinite sum here. So what is happening is I add these numbers forever and ever and ever. And what I want to do is use some technology to complete this a little bit quicker for ourselves. So scroll down to this next page here. And here is that sum of 1 over n cubed, and I'm going to use calculator. I'm going to pull up a TI calculator to do these sums for me. Now the sum of the first 2 terms and the sum of the first 5 terms we already have. Now I'm going to go ahead and use my TI to find those for me. So a couple different ways to do this. The first way that I'm going to show you to do this is I'm going to pull up the summation feature. So that is under the math key. So I'm going to hit the math key, and I'm going to go to number 0. I'm going to go upward, and I'm going to pull out summation. I want to sum the first, let's say, 2 terms of my series. Now what we had been doing is we were saying, n is my variable. So notice I'm in the alpha lock mode, so I got to look for the green. Here's green n right here. So I'm going to say n goes from 1 to 2 of 1 divided by n cubed. Notice it's not in alpha anymore, so I have to hit alpha and then n, and then I will cube that. So here's 1 over n cubed from 1 to 2. Here's the sum of the first 2 terms, and that would have been, let's see, I should be able to do math fraction, and it'll give me the 9/8 that we got. It can typically handle smaller decimals. So we see 1.125 is the value in my first table. So this is the sum of the first 2 terms, 1.125. Now we could, for the sum of the first 5 terms, just scroll back up, take that fraction, convert to a decimal, but I'm going to use my technology. And I want to point out to you on my sheet here, I converted in this table a different index letter. So most textbooks, you'll typically see this when they start to talk about partial sums. So I'm going to sum the first 2 terms. I'm going to sum the first 5 terms, the first 10, the first 100, the first 500. And they eventually say I'm going to sum the first n terms. So they call it like the nth partial sum. So I just wanted to switch letters. It doesn't really matter what letter I use in this sequence. I could use X, could say 1 over x cubed. It doesn't really matter, right? But typically in a textbook, that's what you'll see is I will be my index of my series. So I'm going to go to n. So I want to type it in the calculator this way just to show you a different approach. All right, so I'm going to go math. I'm going to go to 0. Let me just punch 0. So I'm going to sum, and I'm going to use I. And again, it's under the alpha lock initially. So here's I. I'm going to say I goes from 1 to, now we're going to 5. And we're doing 1 divide by I. So I got to do alpha I cubed. Okay. So I hit enter, and that big fraction we had on the first page, here's its decimal form. And actually, will this convert? I'm curious. I bet it doesn't. Nope. It struggles. All right. So I wish I could copy and paste this here, but this is what I would put in the other table. Let me pause and write that. All right, so I just did a quick little copy paste here. So I want to do the rest of these. Now I want to get a little bit more efficient. I don't want to have to keep typing these individually and then copy and pasting them into my table. So I'm going to get a little more efficient here with my TI. So let me bring my TI back up. So what I want to do is use my table feature. I'm going to go to second graph and use my table feature here and just have it fill all of that in for me very quickly. So here's how I'm going to do that. Let me go to y equals. And then in the y1, I'm going to call out the sum feature. So I'm going to go to math. And then I'm going to punch 0, and here's my summation. And again, I can use any letter that I want here, but I'll stick with the I that we were doing. So again, I'm already in alpha. I'm going to hit I, goes from 1. And then what I want, so typically when I'm in function mode, calculator wants y to be a function of x. So I'm going to let my quote-unquote variable, so the upper value of my series is what we are varying. So we're letting this value be 2, and then 5, and then 10. So this is my quote-unquote variable in my table. Right? So I'm going to sum from 1 to x, and I have 1 over I cubed. Okay. Now the other thing I want to do, I want to go to the table set menu. So I'm going to do second window, and I want to put the independent variable in the ask option. So if auto is highlighted, I'm going to arrow over, hit enter on ask. And now when I go to my table's blank. So I can punch in x equals 2, and there's the sum of the first 2 terms. Could punch in x equals 5, there's the sum of the first 5 terms. And then what did I want in my table? So I wanted the second partial sum, fifth partial sum, 10th partial sum. So I'm doing 10, 100, 500. So let me do 10, and then I'll do 100, and then I'll do 500. Look at that. Took a little while for the calculator to figure that out. Now, so if I go back to, my first page, we had those big fractions. Here's my decimal values of those fractions. And again, to point out to you in my TI, it's rounding because it only can show me like 4 decimal places. So I could go over and highlight, and here's all the decimal accuracy. So I may want to keep as much decimal accuracy as possible so that I can really see what my limit is approaching. So let's go ahead and finish off this table then. So I want to do 1,000 and 10,000. I don't know if it can do 10,000. It kind of gets to a point where it breaks down. It runs out of memory on the chip. Ooh, check it out. It did it. Will it do 10,000? I think I might break it at this point. Look how long that's taking. So I think it might not do 10,000. I kind of hope it breaks so I can show you what the error would be. Oh man, it figured that out. That's crazy. All right. Sometimes the memory on the chip in the computer it'll run out of memory. And the error it'll give you is called like a overflow error or a stack error. So that just means we've gone too far. We're trying to add too many terms. But if I go over here and I look at the decimal accuracy, so it looks like we're approaching 1.2021, right? But if I look, it's really 2020074. Here's 2020549. Here's 2020564. Here's 2020568. So notice I got 202056. And here's 202056. So I'm starting to kind of fixate on the first 6 decimal places. And as I add more and more terms, I'm going to fixate on more and more, right? So I'm getting more and more accurate. I'm getting a limiting value in this case. So as I add more and more terms, my infinite sum is converging to this number, right? Whatever that number is. So this is pretty cool, right? Check it out. We've added infinitely many terms, and we have a summation that is finite. So how can I add infinitely many numbers and get a summation that is finite? Great question, and we'll delve into that a little deeper in just a moment. All right, so I paused the video again because I just wanted to fill in the table here just for completeness of our conversation. So we can see the sequence of partial sums is converging, right? As I add more and more terms onto my series, I'm approaching a finite summation. So our sequence of partial sums is converging here. So we're going to say the infinite series has a finite value, right? It is converging. So from the table, what is the limit? We're going to say approximately something like 1.202056. Let's say. Let's go to 6 decimal places. So this was where I kind of started to fixate right here to the 6 decimal place. So I'll just kind of stop there. So there's my infinite sum is approximately that value. And then I just want to also point out to make a connection for something about 5 minutes from now we're going to discuss. If we look specifically just at the terms, so I'm not looking at the sum of the terms, I'm just looking at each term individually. As n goes to infinity, how do these terms behave? And what I'm really getting is 1 over infinity in essence, right? This is really bad. This is not very rigorous mathematically, but conceptually, the term in the denominator is cubic. It grows larger and larger and larger. So I'm getting something constant over something going to infinity, and that goes to 0. Now, if we stop and think for a second, intuitively, if the terms long term, right, if the sequence terms go to 0 long term, then it makes sense that when I add all of those numbers together, they become finite, right? So like way out at the end of the series, I end up getting 0 plus 0 plus 0 plus 0 plus 0 plus 0 plus 0. And so I end up adding things that are negligible, really, really, really tiny. And so my sum kind of stops growing and it becomes finite. So intuitively, this seems to make sense here. Now, what I want to do then is look at a different example. So here's an example, and I want to plug into the technology, and I want to find what the sum of these sequences are, right? So again, I want the sum of the first 2 terms, and then I want the sum of the first 5, and the sum of the first 10, and the sum of the first 100. So I want you to use your technology to do this. I'll pause this video, do this table on your own, answer these questions over here A and B, and when you're done, unpause, and we'll discuss this together. All right, now I want to show you a different approach in regards to technology. I don't know if you can see this. Hang on, let me minimize here. So I went to desmos.com. So I'm using the online free HTML5 based calculator, desmos.com. And so what I did, this is pretty cool, right? So I defined the function that is the infinite series. So I said, let's set f of x equal n going from 1 to x, right? Because again, I want to vary this sum, how many terms I sum. So I'm going to go from 1 to 2, 1 to 5, 1 to 10. So I'm letting this be x, so I have a function of x. Then I have x over 3x minus 1. So the way that I did this, I'll show you down here, I just do function notation. I say equals, and I start to type the word sum, and it brings up the sigma notation. And then once I define that equation, what I then do is I click to add a table, and it adds a table for me. Now here's what it labels the table with. So what I did was I just came over here and deleted the sub 1, and I called this f of x. Okay, and that way I was filling in the values. So as I typed different values of x in here, it filled the table in for me. Right? So here's my table. So if I come back to my Word doc, here's the values in my table. And so let me see. If I copy and paste that real quick. Alright, so I just paused the video again real quick and I came back to my table. So we can see what's happening in this case is kind of the opposite of what we saw in the prior example. Our sums are getting larger and larger and larger and larger. So when I look at this sequence of numbers here, right, this is the sequence of the partial sums. So this sequence is diverging, right? As a limit, these numbers are going to infinity, right? They're not approaching a finite value. So, what is the limit of those partial sums? That's infinite in this case. So this series is diverging, right? It does not have a sum that is finite. Now, if we come back and we just look at the list of numbers here, if I take a limit of just the sequence of numbers, technically I get infinity over infinity here, so I'm going to use L'Hopital's rule. Right? So L'Hopital's rule says take the derivative of the numerator, the derivative of the denominator, and reevaluate your limit. Of course, as long as I have an indeterminate form of infinity over infinity or 0 over 0, I can do this. So now for this example, I get the limit of a constant, which is the constant. So the terms of my series, so what I'm adding together, approaches 1/3. Now intuitively, it makes sense that when I sum all of those numbers, I get a exploding, right, or a growing summation, right, that grows without bound, right? So long term, I end up doing 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3, and forever and ever. So as I keep adding 1/3, I'm going to grow and grow and grow and grow, and my sum is going to be infinite, and that's what we see in that sequence of partial sums there. Okay, so I'm going to do one more example here, and again, I want you to pause the video. I want you to complete this table, and I want you to either use your TI calculator or use Desmos. You notice Desmos was a little more efficient, but either one that you're more comfortable with. So pause, complete this table, answer A and B over here, and when you're done, unpause, and we'll talk about these together. All right, I just caught a mistake. Hopefully you caught as I was talking about that last problem. When I was using Desmos here, I was using the wrong letter in my summation. Right? Remember, the n is what we're plugging into. So I really should have as n over 3n minus 1. So I'm going to fix that. Let's see if it changes the values in my table. Well, it didn't change the values in my table. All right. So when I do this problem, I'm really doing 1 over n. Is what we had in that formula, right? So we had 1 over n that we were summing, n going from 1 to infinity. So just fixing that symbolically to be correct. So summing up 1 over n, and we can see that it looks like my sum is growing and growing as well. I'm going to go a little further out. Let's go to 100,000. Okay, and it definitely looks like I'm growing. So I'm going to go to 1 million, and it's getting bigger and bigger. So 10 million. Absolutely. All right, so in my limit of the sequence of partial sums, that is growing and growing and growing and going to infinity. Let me pause and copy and paste this for our Word document. All right, so I paused just so I could do a copy and paste here. And so from the table, we can see that our infinite sum is going to infinity. Right, so this infinite sum is going to infinity. My series is diverging. And then what is the limit of the sequence? So when I look at just the numbers, 1 over n, right, this is behaving like 1 over something growing without bound, and that's going to go to 0. Now for comparison, back to our first problem here. When we looked at our first problem, the terms 1 over n cubed went to 0, and our summation was finite, and we said that made sense intuitively because we ultimately get 0 plus 0 plus 0 plus 0 plus 0, and so my sum stops growing. And we're noticing something that is different from that. In this example, my terms also go to 0, but my summation is diverging. So this is interesting. So here's the case where I end up getting 0 plus 0 plus 0 plus 0, but my sum continues to grow. So why? Why is that the case? That's a great question, right? And we'll take that a little bit deeper in the next video. But basically, in layman's terms, in order for my sum to be finite, in order for my infinite sum to converge, the terms have to go to 0. But they also have to go to 0 fast enough. And again, that's not mathematically rigorous, right? But in layman's terms, my terms of my series have to go to 0 fast enough so that when I add them together, the summation becomes finite. Now, we will always see the case that if the terms don't go to 0, I will always get divergence. And again, if the terms don't go to 0, I end up getting 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3 forever and ever and ever and ever, and that sum is just going to continue to grow and grow and grow. Now, if we look at this sequence of partial sums, notice how quickly this exploded, right? This grew without bound very fast. And let's look at this series. It didn't grow very fast at all. Check this out, right? So it diverged, but very slowly. We're all the way out to, what was this, 10 million, and I'm only still at a sum of 16. So what's happening, again, these terms, the terms of the series are not going to zero fast enough. And we can see the summation, right, the sequence of partial sums is diverging. So just to wrap this up for a moment here, and every calculus textbook you have is going to, at this point, formally define the convergence of a series. So again, in the prior video, we talked about the convergence of a sequence, and what we said was if the terms in the sequence approach a finite value, right, if they have a limit that exists, then the sequence is converging. So what we've done in this prior conversation for 15-ish minutes here was we took a summation and we looked at the partial sum. So we looked at the sequence of partial sums. So basically we would say, something along these lines. Let's say for the sum of a sub n as n goes from 1 to infinity, we consider the series of partial sums, or the sequence, we consider the sequence of partial sums right? And we'll call that S sub n, right? And then if the sequence of partial sums has a finite limit, then we say the series converges, right? Then the infinite series converges, right? Otherwise, the series diverges, right? So if the limit doesn't exist or is infinite, then we would say it's divergent. All right, so here's kind of a formal definition you'd see in a calculus textbook, and that's just what we explored in those three prior examples. We looked at the sequence of the partial sums, and we could see from that sequence of partial sums whether the sequence was divergent, so whether the sums were getting bigger and bigger and bigger. Okay, so typically in a section like this, at this point, we introduce what we call the test for divergence. So the test for divergence basically says that if the terms of the series don't go to zero, then when I add them all together, that's going to be divergent. Now again, we just said a couple minutes ago that if the terms do go to zero, we might get convergence, we might get divergence. Right? So if the terms go to zero, they got to go to zero fast enough. However, if the terms don't go to zero, then we know the sum will always be divergent. So again, we have what we would call the test for divergence. Some books call this the divergence test. So one of the first tools we will use, so kind of when we get to the end of a chapter like this, one of the first tools we will use to determine if a series diverges or not is we would just look at the list of the terms in the sequence, right? So in other words, when I look at this example, when I'm looking at these terms here, so what is the limit of n over 3n minus 1? And, we did this one already, right? This was the second one that we built in the table. Right, so this was 1/3. I'll just jump to that result. So since this is non-zero, then the series diverges. Right? And technically we would say the series diverges by the divergence test. By the divergence test. Okay. So again, just as like mentioned a couple minutes ago, ultimately as we go look long term, we got 1/3 plus 1/3 plus 1/3 plus 1/3, and this summation is going to diverge. Right? So again, that's what the divergence test says. If the terms don't go to zero, then when I add them, they diverge. So the next problem that I had on here was show that this diverges. So my instruction said show that this diverges. So we know it's divergent. We know that the limit will be non-zero. So I want you to pause the video for a minute. I want you to take the limit of 3 to the n over 2 to the n minus 3 and show that that will be non-zero. So pause, try that, and then come back and unpause. All right, so now that you have tried on your own, when we think about each of these, like the numerator and the denominator independently. So the numerator is like an exponential function. It's like 3 to the x. So we know that an exponential, when the base is bigger than 1, grows to infinity. So we know that that's infinite. And then the denominator is like 2 to the x. So again, exponential, base is bigger than 1, it grows to infinity. So we can use L'Hopital's rule if we desire. That's what I prefer to do. So I'm going to take the derivative of the numerator. So the derivative of 3 to the x is 3 to the x ln of 3. So the derivative of 3 to the n is going to be 3 to the n ln of 3. And then when I differentiate 2 to the x, same thing. Derivative of 2 to the n is going to be 2 to the n, and then it's ln of the base. Then the derivative of the minus 3 is 0. Now when I look at this limit, the way that I like to think about it is ln 3 over ln 2 is constant. So I'm pulling ln of 3 over ln of 2. That should be an ln. ln of 3 over ln of 2 is constant. Let me get rid of that equal sign real quick. So I pull that out of the limit process, and then I have 3 to the n over 2 to the n. Now what I'm going to do with this right here is I'm going to write this. I'm going to leave a little room. Use my properties of exponents that says that's 3 halves to the n. The limit is n goes to infinity, and I have, have my constant. Let me just write my constant out here. Now in the prior video we talked about this being a sequence that was geometric, right? And this is like an exponential function, right? This is like, a to the x power. And just like we saw up here, a to the x or a to the n increases when n is greater than 1, right? So it increases to infinity. So this is going to go to infinity, and the symbolism we used in the prior section was that the common ratio of my geometric sequence is 3 halves. Since that's greater than 1, it goes off to infinity. So again, this limit is non-zero, and therefore the series diverges. All right, so do one more for me here. I want you to take a look at this guy. Here's a divergent series. Use the test for divergence to show that this diverges. Pause the video, try this on your own, and then come back. All right, so let's talk about this one together now that you tried it on your own. So again, we are doing the limit as n goes to infinity of cosine of n. Now this limit is going to be, I'll say equals does not exist. So how do I, come up with that result? If we think visually for a moment, think back to the continuous function cosine. Looks something like this, right? Now, granted, as we've discussed before, right, these aren't continuous functions that we're dealing with here. Cosine of n is just a discrete collection of numbers. Those aren't continuous, right? They're a discrete defined function. So I'm not really looking at the continuously defined cosine curve, but these terms, cosine of n, are numbers that are just going to kind of oscillate up and down. So as a function, as a list of terms, they're not approaching one single number, right? I mean, if we think about a function that approaches a number, that's not what we're seeing here. We're getting terms that just kind of oscillate. So it's not going to infinity. It's not approaching a specific number. There's just not one single number. So just like back in a Calc 1 class, cosine and sine, as we go to infinity, don't have a limit that exists. So that's a does not exist. Right? That is not equal to 0 in essence, and so this diverges by the test for divergence. Right? Okay. All right, so just to summarize again what we've been talking about here is the test for divergence is what we have explored. Right? So for the test for divergence, right, it basically says something along these lines. Right? That if the terms of the series don't go to 0, right? So I'll say if the terms, right, of the sequence, right, if that is infinite or does not exist, then when we add those terms together, I am so sorry, let me say that that is non-zero. That's how we're going to state this. Right? If the terms are non-zero, or do not exist, right? If the limit of those terms are non-zero, do not exist, then when we add all of those terms together, that series, infinitely many terms being added, is divergent. Now, what we saw earlier, right, one of the things we talked about, and you'll usually just see this in a textbook, and it's not given a name, just usually said that it's a theorem. And it basically says that if a series does converge, then it has to be true that those terms in that series, right, the numbers that we're adding together, they had to go to zero. So the only way a series will ever have a chance of converging is if the terms go to zero. Now again, in that worksheet, we saw two situations. One, the terms went to zero and the series converged. I think it was 1 over n cubed that we looked at. And the other, we looked at the sum of 1 over n. Those terms also went to zero, but that series diverged. Right? So we always want to be careful here. Just because the terms go to zero doesn't guarantee convergence. And we talked about really the terms have to go to zero fast enough, and we'll get into that deeper later. But if we know the series converged, then it had to be true that the terms went to zero, i.e. fast enough, okay? So if the terms don't go to zero at all, then we know when we add them together the series diverges. Now typically the last thing we would see in a section like this is a conversation about the geometric series. So let's discuss that for a couple of minutes and take a look at some examples. So in the prior section, we talked about a geometric sequence. Now we're going to talk about adding all of those terms together to generate a geometric series. Now, typically, the way most textbooks write a geometric series is we'd have a plus a times r plus ar squared plus ar cubed, and so on and so forth. So one way that we can describe this series is say it's the sum of ar to the n minus 1 as n goes from 1 to infinity. Right? So if I let n equals 1, I get r to the 0. Anything to the 0 is 1. So I get a as the first term in my series. And then when n equals 2, 2 minus 1 is r to the first power, and there's our next term. And when n is 2, I'm going to get r to the, I just said n is 2. When n is 3, I'm going to get 3 minus 1, or r squared. ar squared is my next term, so on and so forth. Now, when I look at something like this, so as an example, I'll look at, let's say, negative 1/2 to the n minus 1, let's say, and goes from 1 to infinity. So when I write these terms out, right, when I plug in n equals 1, I get n minus 1 to the 0, which is 1. And then plus, when n is 2, I get 2 minus 1, which is 1. I get negative 1/2. Then when n is 3, I get negative 1/2 to the 3 minus 1. Negative 1/2 squared is positive 1/4. And then I'm going to get negative 1/8, and so on and so forth. So for me, mentally, right, when I look at the terms of a series, if the terms are exponential in essence, then this is most likely geometric. And when I say exponential, if I look back up at our generic form, right, I take the first term here, multiply by r, and I get the next term. And then when I take that term, I multiply by r, I get the next term, so on and so forth. So each term is r times the prior term. So usually what we'll do here is we call that the common ratio. So I'm going to come back up here and say the common ratio. And technically, one way to write this is that the common ratio, let me say it this way. We'll say that the next term is the prior term times r. So for example, again, if I look right here at the fourth term, ar cubed, I got this term by taking the prior term and multiplying by r. And that is true for any pair of adjacent terms. So the next term comes from the prior term times r. And, so for me, visually, I look at this as like a multiplicative factor, right? So I multiply every term by the common ratio. If I look down at this example, my common ratio here is negative 1/2, right? Based on how we write our series form for a geometric series, right? So my common ratio is negative 1/2 here, and we can see, 1 times negative 1/2 is negative 1/2, so I get the next term. Negative a half times negative half is positive a quarter, so I get the next term, and then positive a quarter times negative 1/2 is negative 1/8, so on and so forth. So we're generating really an exponential behavior, right? This is like, r to the x, if you will, right? We write it as r to the n minus 1. Now, most textbooks, instead of thinking of the r as the multiplicative factor to get the next term, what they typically do is they let's say we solve for r right here. We get a sub n plus 1 over a sub n equals r. So this is usually how you see the common ratio defined within a textbook, calculus textbook, or sometimes a pre-calculus textbook. And this is where it gets the name common ratio, because this ratio, right, of two adjacent terms is what my r value really is. So if I take any two terms that are next to each other and I divide them, I'm always going to find that common ratio. Now notice that in this definition, right, the later term is divided by the prior term. So for example, if I come down here, my series, if I take negative 1/8, I divide by the one right before it, that's going to give me my r of negative 1/2 here. So this is the generic form of a geometric series. We talk about the common ratio. Here's an example of a geometric series here. Now, back in the section on sequences, we developed the idea that for a geometric sequence, the geometric sequence will converge as long as, r is less than 1. And if I scroll back up here for a second, let's take a look at this example just to discuss this real quick, right? If this number right here, if the base is bigger than 1, right, let's suppose it's 2 to the n minus 1. Right, this is just going to get bigger and bigger and bigger and bigger. I'm going to get 1 plus 2. I'm going to get 2 squared. I'm going to get 2 cubed, 2 to the 4th, so on and so on and so on, right? So look how large these numbers are getting. There's 1 plus 2 plus 4 plus 8 plus 16. So when I add that forever and ever and ever and ever, that sum is just going to explode, right? It's going to grow without bound. And if we think of our test for divergence, if I do the limit of 2 to the n minus 1 as n goes to infinity, right, the limit of those terms is non-zero. So the test for divergence would tell me very quickly that this series is divergent. But if we just think back to, kind of our intuition from an algebra class, this is like an exponential function, right? That's what we see here. 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th. This is like 2 to the x as an exponential function. So we know that an exponential function is going to grow very quickly when the base is bigger than 1. Right? So if we just kind of connect back to that idea of an exponential function, right, we know that y equals, I'm going to call it, r to the x, let's say. If r is greater than 1, that's going to grow to infinity. Right? All right, and then, in an algebra class, right, we would then look at an exponential function that decreased. So this was r to the x if r was between 0 and 1. Right? So that went to 0. So if my r value, my common ratio is, fractional, let's say, less than 1, between 1 and 0, then my terms are going to go to 0. And have a chance of converging. And if the terms are greater than 1, the common ratio is greater than 1, it is going to diverge. Now, again, keep in mind, we talked about this earlier, right? I'm not really looking at continuous curves here. I'm looking at discretely defined functions. So 2 to the n would just be the discrete points that lie along this curve. Right? So 2 to the n is only defined when n is 1, n is 2, n is 3, so on and so forth. But we can kind of connect mentally to the idea of the continuous curve, right? So here would be, 1/2 to the 1, 1/2 squared, 1/2 cubed, 1/2 to the 4th, right? So if the base is fractional, the terms are going to 0. All right, so what we usually see in a textbook here is that the series, the geometric series of a r to the n minus 1, and going from 1 to infinity, all right, this will converge if the base, I don't want to say a, my base is r here. So if the base in absolute value is less than 1, so in other words, any number, right, between minus 1 and 1, it will converge, and it will diverge if r is greater than or equal to 1, right? So anything where I get exponential growth here. So what I'd like to do for a moment here is kind of go through a little derivation conversation, and let's talk about why this result is what it is. And the reason that I want to do that, it is then going to connect to something very unique, which is finding the exact sum of a geometric series. All right, so in order to prove convergence for the geometric series, what we're going to do is what we did at the very beginning of this video. We're going to consider the sequence of partial sums. So back in the very beginning, we looked at a table of values, or we looked at the sequence of all of the partial sums, and we were investigating whether that sequence of partial sums had a limit that existed, right, if it was converging. So we would do the same thing here. Now in a derivation type of form, and I don't want to use specific numbers or examples like we did in the very beginning, right? In the very beginning we looked at 1 over n cubed. We look at a specific form. So what we're going to consider here is the following. We showed the form of the geometric series, and what I want to consider is just summing up the first n terms for the geometric series. So I'd have a plus a times r plus ar squared plus ar cubed plus so on and so forth. And let's say we stop at the nth term here. And technically this would be ar to the n minus 1. Right? So this was the n equals 1 term, so that it was n minus 1. Right? So these are all up to the n minus 1. So to show convergence here, we're going to do something pretty unique. And a lot of these tricks for summing up series, finite series, came from Gauss. So what's really unique that we can do here, we can take my sum of my first n terms and let's multiply it by r. So if I just take r and I multiply it, I distribute it into this finite sum, I'm going to have a times r. And then I'll have r times the second term, ar squared, and then r times the third term, ar cubed, and then ar to the fourth, and then out to, now technically I'm going to have an ar to the n minus 1, and then an ar to the n. So when I multiply this last term by r, I add the exponents, right? R to the n minus 1 times r to the 1, and that's going to give me n minus 1 plus 1, which gives me just r to the n there, okay? So in essence, when I multiply every term here by r, I'm bumping everything up one exponent, right? Now, what I could do here, this is kind of cool. I'm going to think of this as a system of equations. So here's two equations that I have. One equation is the nth partial sum. The other equation is r times the nth partial sum. And I'm going to subtract these from each other. Now, when I subtract these from each other, think about what's going to happen. I'm really changing the sign of every term here, and I'm adding. So I'm going to think of taking the first equation, I'm adding the negative of the bottom equation. And notice that I'm going to get ar minus ar, and I'm going to get ar squared minus ar squared. I'm going to get ar cubed minus ar cubed, and there'll be an ar to the fourth, and that'll subtract. And then the ar to the n minus 1 will get subtracted out, and I'll be left with ar to the n and just the a term. So if I take my nth partial sum and I subtract r times my nth partial sum, I get just the first term that survives in that subtraction, and then I get minus this last term. Remember, I'm subtracting that off. Okay. So here's the difference of the two, and then I'm just going to do a little bit of algebra here. I'm going to factor the nth partial sum symbol here, and I'm left with 1 minus r. And then I'm going to go ahead and take the a out of this as well and write this as 1 minus r to the n. And then if I solve for my nth partial sum, which is what I'm really interested in here, I get this expression. So this is a formula that gives me the sum of the first n terms for any geometric series. Now, if I remind myself, I'm summing up the first n terms. So this is not the sum of the infinite series. This is just the sum of the first n terms. So if I come back to my first example where I had negative 1/2 to the n minus 1, let's suppose we wanted to sum up the first 10 terms, then I would plug in n equals 10. I would plug in my r of negative 1/2, and the a represents the very first term in the series, right? The very first term that we had. So, again, just to illustrate this formula, right, if I consider back to my example, negative 1/2 to the n minus 1, right, as n goes from 1 to infinity, right, that was 1 minus a half plus a quarter minus an eighth, right, plus dot, dot, dot. So if I wanted to look at the 10th partial sum, so the a in my formula is that first term, and then 1 minus r. My r is negative a half. And then the 10th partial sum, that would raise that to the 10th. And I would divide by 1 minus my r value. So, in this case, I would have 1 minus, raising this to the 10th power makes this positive. So I could write this as like 1 over 2 to the 10th. Right? And then let's see, 1 plus a half is 3 halves. So that's going to be a lovely number there. Let's see. If I flip and multiply this, I'm going to multiply up here as 2/3, let's say. So I would have, what? Let me get a common denominator for this guy as well. 1 is going to be 2 to the 10th over 2 to the 10th. So I'm going to have 2 to the 10th minus 1 all over 2 to the 10th. And then I am flipping and multiplying by 2/3. So one of these 2's cancels out here, and this becomes a 2 to the 9th. So I have 2 to the 10th minus 1 over 3 times 2 to the 9th. Right? So there would be the sum of the first 10 terms for my finite geometric series, negative 1/2 to the n minus 1. And I could plug that in a calculator and find out that value. Now remember, ultimately, here's what we're really interested in. I got a little sidetrack there, went off on a tangent. Ba-doom, boom. So I'm really looking at, here's the sum of the first n terms. What I'm really interested in is as n goes to infinity, right, what happens? So two things are going to come from that. One, we're going to see that the only time this limit is finite is when my common ratio is less than 1, which is what we said earlier, right? We said those series converge if r is less than 1. We're going to see that happen here in just a second. And it's going to produce a formula that finds the exact sum for us. All right, so let's come down here then, and let's take a look at the limit of that nth partial sum. Right, so when does the series converge? Right? When does it converge? When does a r to the n minus 1 converge? Right? Question mark. So we're looking at the limit as n goes to infinity of that partial sum. Right? So that was a 1 minus r to the n all over 1 minus r as n goes to infinity. Now the only thing that really involves the limit is the expression that has the n on it. Right? So I'm really looking at r to the n as n goes to infinity. And there's a couple properties of limits that I could use here. I'm just going to mention them verbally. But the limit of a quotient is the quotient of the limits. So I'm technically taking the limit of the numerator and the limit of the denominator. But 1 minus r is constant in regards to the n that our limit is looking at. So, this is just constant. Right? This is constant. I'm doing the limit of a difference. The limit of a minus b is a limit of a minus a limit of b kind of thing. So ultimately, a couple lines of work that I have here, what I'm really looking at is just the r to the n expression. That's what is not constant in the limit process. So how does r to the n behave? Well, again, in the prior video for 11.1, we kind of made the connection to exponential functions here, like we talked about a couple minutes ago. So when this base of the exponential is less than 1, this will go to 0. And when this base is bigger than 1, this will go to infinity. So the only time I'm going to get convergence here, right? So let me scribble this down here in a different color. Right? So we have, we know that the limit of r to the n goes to 0 if r is less than 1, right? And the limit of r to the n will go to infinity if r is bigger than 1. Okay. All right, now, So if this term is going to 0, let's say, right? So if this term is going to 0, then what we end up with in this case is we're going to have a times 1 minus 0 over 1 minus r. And so we get a over 1 minus r. So this is like my infinite sum, right? I have taken the limit as n went to infinity. So remember, I took the nth partial sum. So I took the sum of the first n terms. I let n go to infinity. So I added infinitely many terms. And I end up getting a over 1 minus r, only if r is less than 1 is where that will converge. Now this is really, really cool because all of the other series that we're going to talk about, we can't find the exact sum of the series. We can only estimate. And then we talk about the error that comes from that estimation. So this will be the only series throughout this whole chapter where we can discuss the actual sum. We can sum all infinitely many terms, and we can find exactly what that summation will be. This is really unique. We're going to use it to our advantage a couple other times in future videos, future sections. So again, this does two things for me. This tells me why the geometric series converges where it does when I look at the sum of the first n terms here. And then it tells me what the actual sum of infinitely many terms is. That's really cool. Okay, so again, just to summarize what we said there, the geometric series, the sum of ar to the n minus 1. This converges if the common ratio is less than 1 and has the sum of a over 1 minus r. And again, remember, a is the first term in that series, and r is the common ratio. So really, really cool, nice, clean result, and we'll use that quite a bit in the near future. And what I want to do, this video is getting kind of long here, and I apologize. This is a really crucial section where we lay the groundwork. I should say convergent. Right? This is a really crucial section where we lay the groundwork for all the remaining sections we're going to do. So just wanted to take time here to really talk deep about this. So this last piece, this geometric series, right? Let's do an example or two where we kind of see this in action. We're applying this knowledge that we just wrote. All right, let's suppose we have a couple homework problems, and it says something like this. Let's say determine whether the geometric series, sorry for my sloppy handwriting here, determine whether the geometric series converges or diverges. And if it converges, find its sum. Right? So I just save a second of time here. If it diverges, obviously it has no sum, right? But if it converges, then it does have a sum, and let's find what that summation is. Right? So let us say the first one we want to look at is, let's say 3 minus 4 plus 16 thirds minus 64 ninths plus dot, dot, dot. Now, when I look at this example, I've been told that it's geometric, so I'm kind of looking for that pattern. And, like I mentioned to you earlier, what I like to think of is like, what do I multiply 3 by to get the next term? And then what do I multiply negative 4 by to get the next term? And what do I multiply 16 thirds by to get the next term? That's not always obvious, so we could think of that definition that the common ratio comes from dividing two adjacent terms. So if I take the term of negative 4 and divide it by the prior term, that actually gives me my common ratio. And just to show you that that's true, right, let's take two other adjacent terms. Let me take negative 64 ninths, and let's divide by the term prior, so positive 16 thirds. Right? And if I flip and multiply negative 64 ninths times 3 over 16, we're going to reduce and get negative 4 thirds there. Okay? So, the 3 and the 9 reduce to a 3, right? And the 16 goes into 64 4 times. And there's our common ratio. All right, now in regards to the geometric series converging or diverging, we need that common ratio to be less than 1. So, we'll just kind of make a note here that the absolute value of r is, the absolute value of -4/3. That's positive 4/3, and that's greater than 1. So this series is divergent. I'm just going to come down here and say that it diverges. So there's no way that we're going to waste our time to find the sum of that series because it doesn't even converge. And the sum would just grow and grow and grow without bound. It's never going to be finite. Okay, let's take a look at another example. Oops, this thing is so jittery. All right, so let's say second example is, let's do one that's kind of fun like this. All right, so let's just write it in sigma notation and say that I have -3 to the n minus 1 over 4 to the n. And n goes from 1 to infinity. Now we're being told that this is geometric. So I could write the terms out here, and I'm going to do that just to explore, but then I'm going to come back and just do a little bit of rules of algebra. But if I plug in n equals 1 first, I'm going to get, -3 to the 1 minus 1, -3 to the 0 is 1, and then I get over 4 to the 1. And then plus, when n is 2, 2 minus 1 is 1, so I get -3 in the top. And then I get 4 squared in the bottom. I'll just say 4 squared. Obviously, that is 16. And then when I plug in n equals 3, I get -3 to the square. Right? So that's positive 3 squared, which is 9, right? But I'll just write it as positive 3 squared. And then I would have 4 cubed. And then plus, and then again, when I plug the next value of n, it would be n equals 4. I'm going to have 4 minus 1, which is 3. So I have -3 to the 3, which is -27, but I'm going to write it as -3 cubed over 4 to the 4th, and so on and so forth. So we can see in this case that the first term is 1/4. That's my quote-unquote a number. And then what did I multiply this by to get the next term? I multiplied by -3 over 4. So when I multiply this by -3/4, I get the next term. I multiply this by -3/4, I get the next term. So my common ratio is -3/4. Now how would I see that out of this series? So just make a little note down here to see this algebra. So if I just look at these terms, I just want to ignore the sigma notation for a moment so we can do a little bit of algebra here. Now remember that what Stewart likes to do, scribble down here, right? He likes to write the series as a r to the n minus 1 as n goes from 1 to infinity. So what I'm going to do is a little bit of algebra magic, right, to get this to look like this form. Right? So the way that I'm going to do that, I want this to be 4 to the n minus 1. So what I'm going to do is multiply, I'm going to take -3 to the n minus 1 over 4 to the n. And I'm going to multiply in the bottom by 4 to the -1. And I'm going to multiply up top by 4 to the -1 as well. So I'm multiplying by the number 1. And the reason that I multiply in the bottom by 4 to the -1 is when you think about this, our properties of exponents say when I multiply like bases, I add the exponents. So when I multiply 4 to the n and 4 to the -1, what I get is 4 to the n plus -1. So I'm adding exponents when I multiply like bases, and I now have -3 to the n minus 1 up top. And then I'm going to take this 4 to the -1, and I'm just going to leave it here for a moment. Now, all of this, right? All of this I can do a property of exponents like we've done before, and I'm going to take, a to the power over b to the power, and I'm going to write it all as -3 over 4, all to the n minus 1. Right? So that's a property of exponents. When my exponents match, I can just pull and divide the bases. And then I have times 4 to the -1, which is really 1 over 4. So I'm going to put the 1 over 4 out front. So what we've done in this case is we've actually taken our series and we've put it into the generic form that Stewart likes. So we've got our r to the n minus 1, and that's what we said that our r was up here, right? Our r was -3/4, and then here's my a. There's my first term of a. Right? So a little bit of fun with algebra. and we can make the connection to Stewart's formal way that he writes that geometric series. Now we can see in this case that the geometric series will converge. Right? So the series converges, right? And the reason why is r is less than 1, right? So absolute value of r is absolute value of negative 3/4, and that is positive 3/4, and that is less than 1. And since it's converging, then we want to find the sum. So we had the formula that sum was a over 1 minus r. So our a was our first term of a quarter, and then 1 minus the r value of negative 3/4. So let's see, I got a quarter over, this is really 1 plus 3/4. The 1 is really 4/4 plus 3/4. So I really have 1/4, and I'm going to go ahead and flip and multiply. This is really in the denominator 7/4, which is flip and multiply. The 4's cancel, and we get 1/7 as the exact sum of the infinite series. All right, so again, I want to point out to ourselves, geometric series are the only types of series where we're going to be able to find the actual sum of all infinitely many terms. We will not be able to do that for any of the other series that we look at in this class. All right, that really technically finishes everything in this video, but I want to take a look at one more example because it's really, really fun. And it connects back to something that, we've known for a long time and just never made the connection to. Right? So this is really fun. So the last example here is I want to show that the number 0.99999999999 repeating, right? Let's show that that exactly equals 1. So what we're going to do is turn that repeating decimal into a geometric series. Now, if we stop and think for a second, if I only look at the first term, let's say the first decimal value, let me cover this up here. If I only look at 0.9, 0.9 is approximately 1. And if I look at the first two decimals, 0.99 is a better approximation to 1. And then 0.999 is an even better approximation to 1, and 0.9999 is an even better approximation to 1. When we let that repetition go forever and ever and ever, infinitely many times, that actually equals 1. So if we think about 0.9999999, what that really is 0.9 plus 0.09 plus 0.009. Right, so we're really adding a 9 into each decimal place is what we're doing. So I'm just taking a look at the repeating decimal as being a sum of, right, an infinite sum of 9s being added into each decimal place. If you think about this for a moment, this is 9/10, this is 9/100, right? This is 9/1000, this is 9/10,000, so on and so forth. So what we really have is a geometric series there. And this is, I could write this as 9 over 10 to the first, 9 over 10 squared, 9 over 10 cubed, 9 over 10 to the fourth, dot, dot, dot. So we can see this definitely is geometric. I'm taking the first term of 9/10, I multiply by 1/10 to get the next term, then I multiply by 1/10 again, and then I multiply by 1/10 again. So this is geometric. The r is 1/10, and because that's less than 1, I want to be careful. The r is 1/10. I want to state this a little bit more specifically, right? And since the absolute value of r would be less than 1, right, this is convergent. Okay. Now, what's the sum of that convergent series? So the sum is going to be a over 1 minus r, where a is the first term. So my first term is 9/10, and then 1 minus, and then my common ratio is 1/10. So we can see in the denominator, the number 1 is 10/10. So 10 minus 1 is 9/10, right, over 9/10, and there's the number 1. Isn't that cool? That is so cool. All right, so we just took an idea we've known for a long time, and we have justified using a geometric series that 0.9 repeating forever and ever and ever and ever and ever is an infinite sum. It's geometric, it's convergent, and its exact sum is 1. That's so cool. I love that. All right, so your next Thanksgiving holiday, you got the whole family gathered around the table, and you say to them, "Hey, I can prove to you." So you say, really, like, "Do you think 0.9 repeating equals 1?" And I guarantee you, most people are going to be like, "No, what are you talking about?" And then you bust out geometric series, you blow their minds. First, you make everybody bet, or put some money on the table. Hey, I bet you $10 that I can show you 0.9 equals 1, and you clean up, and you have a good Thanksgiving day. So something else I like to do here, I showed this to my 12-year-old, and I actually didn't go into geometric series, but I just showed the pattern of something that we could prove via long division. So, think back to, 3rd grade, where you learned that if I take 1 divide by 3, and I literally do this long division, I get 0.33333 repeating. And then if we do the long division of 2 divided by 3, we get 0.666666 repeating. So we've just known for a long time 0.3 repeating is exactly 1/3. 0.6 repeating is exactly 1/9. So if 0.3 repeating is 1/3, 0.6 repeating, I said that wrong, 0.6 repeating is 2/3, then why wouldn't 0.9 repeating be 3/3, which is 1, right? So if you do all that geometric series stuff and your family's still like, "Oh, what kind of magic was that? That's witchcraft. I don't know what you're talking about." Bust out this explanation, and then this you can't deny. So the next conversation we want to have in this section is to look at what we call a telescoping series. So I'm going to write out an example here, like I like to do, and then we'll come back and we'll kind of generalize the conversation. But let's suppose that we have the following series. Say we have the sum of 1 over n minus 1 over n plus 1. So we have a series given to us in this form, and let's say n goes from 1 to infinity. So this is what we would call a telescoping series, and let's write out some of the terms in this series to see why it would have that name. So if I plug in values of n, we're going to begin substituting values of n here. So if I plug in n equals 1, I get 1 over 1 minus, and then I'd get 1 over 2. So they would be technically the first term of my series. And when I plug in n equals 2, I would get 1/2 minus 1/3. Then if I plug in n equals 3, get 1/3 minus 1/4. If I were to plug in n equals 4, and so on and so forth. And the reason that we call this telescoping is because we're going to notice a unique cancellation pattern here. And what my series has really, where it has come from is by using partial fraction decomposition. So I'll look at another example a little deeper here, but this original expression that we wrote down here was really developed by using partial fractions on an expression that was rational. But back to the idea of the telescoping. So we're writing out the terms here, and notice that there's a unique cancellation that's happening here. So the negative 1/2 and the positive 1/2 cancel. The negative 1/3 and the positive 1/3 cancel. The negative 1/4, the positive 1/4 cancel. Then the negative 1/5, and there's going to be a positive 1/5 here, cancel. And that cancellation pattern is going to continue and continue and continue forever. So as it turns out, this series just equals this very first term of 1 after all of those other terms cancel out. Now, we know that the series is converging just by exploring and looking at this list of terms, where we see every other term is going to cancel except that first term. So it is a convergent series. Now, technically, what we're supposed to do is the sequence of partial sums like we have discussed earlier in this video. So if I think of the sequence of partial sums here, so let me write this down here. So my sequence of partial sums, we can see, and actually, you know what I'm going to do? Hang on a sec. I want to write out a couple more terms before I get to this conversation. So let me keep writing out some terms here. So I'm going to say plus dot 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 plus. So I'm going to have the n minus first term. So if I plug in n minus 1, I'm going to have 1 over n minus 1 minus 1 over, and this is going to be n minus 1 plus 1. And when I plug in n, I'm going to get 1 over n minus 1 over n plus 1. So let's call this my nth partial sum. Right? So I'm going to come back here and erase my equal to sign. And I'm going to say my nth partial sum is equal to this. So if I'm looking at this as my nth partial sum, here's the sum of my first n terms. We see that cancellation pattern continue as we discussed a second ago. So the cancellation pattern I see here is I have like the last term and then the first of the next term. And then I have the last number in that term and then the first of the next term. So I know the last number in this term canceled with the first in the next term. So in other words, the first in this term canceled with the last in the term prior. And then the last in this term cancels with the first of the next term. And so this term here, the minus 1 over n plus 1, survives, if you will. Right? So this guy survives and this guy survives. So technically, my nth partial sum is 1 minus 1 over n plus 1. And when we talked about convergence earlier in this video, where we looked at the sequence of partial sums, right, we were looking really as, you know, the actual sum is the limit of my sequence of partial sums. So if I look in this particular example, we can see that 1 over n plus 1 is going to go to 0 as n goes to infinity, and this whole series equals 1, which we said already it would just be the first term that quote-unquote survives all of the cancellations. I mean, usually in the textbook, right, we've just had a conversation about sequence of partial sums. So you're typically going to see the conversation being, let's look at the nth partial sum of this telescoping series. And the reality is, if the series is telescoping, it is going to converge because there will be some pattern of cancellation, and the things that don't cancel, or the things that survive that pattern, will be the sum of that sequence of partial sums, or will be the sum of the infinite series. All right, so I want to look at a couple other examples here. Now for this one, I jumped right to us having the already broken down series, and we didn't have to do, partial fractions on it. Right? So another kind of classic type of example you might see in a textbook or a homework assignment might be something like this, right? So let's suppose we have the series, let's say, have the sum of 2 over n squared minus 1, and n goes from 2 to infinity. Right? I want to point out that we're starting at 2 because I can't start at 1. If I start at 1, I get division by 0. So I'm starting at 2 so that this series isn't undefined in that first term, let's say. Right? So let's express the series as a telescoping series. Let's express it as a telescoping series and find the sum. All right, so since this is a telescoping series, I know there's going to be a pattern of cancellation here. Now, I'll point out to you that if I were to just write these terms out as they sit, right? So if I plug in n equals 2, I get, what do I get? I get 2 squared minus 1, so 4 minus 1 is 3. And if I plug in n equals 3, 3 squared is 9 minus 1 is 8. And if I plug in n equals 4, see 16 minus 1 is 15. And if I plug in 5 squared is 25 minus 1 is 24, so on and so forth. Now what we talked about earlier in the video was, as long as all of these terms are going to 0, I have a chance of convergence. There's no guarantee that it converges. Right? We discussed that earlier in the very beginning of this video. Now, we also discussed the test for divergence, right? That if these terms are not going to 0, then the series is most definitely diverging. But I can see that these terms are getting smaller and smaller and smaller. It appears they're going to 0. Right? In fact, if I look at 2 over n squared minus 1, and I look at that limit, as n goes to infinity, I'm getting basically 2 over infinity, and that's going to go to 0. Right? So from the test for divergence, there would be no conclusion here about whether it converges or diverges. Right? So the test for divergence would be inconclusive. All right, anyway, we're told in the instruction here that the series is telescoping. So let's do partial fractions on this telescoping series. I'm going to do a little bit of side work here. So we have 2 over n squared minus 1 that I'm going to split up here. So let's do partial fractions. So blast from the past. Right? It's been a while since we've done partial fractions in our integrating chapter. So if I have 2 over n squared minus 1, I want to factor n minus 1 and n plus 1. Right? So once we factor everything in the denominator, we look at each linear factor. And whenever the denominators are linear, the numerators get constant expressions. Right? Remember, if this denominator here was n squared plus 1, that doesn't factor. So because n squared plus 1 would be quadratic, we would put like bn plus c in the top, right? 1 degree less. Anyway, I don't want to spend 30 minutes reteaching partial fractions, right? Go back into that integration chapter video if you need that refresher. And I will be honest with you, in a section of this nature where we're focusing on series, the goal here is to not, beat you over the head with more partial fractions, but just to show you that we can have a unique behavior of a series, and we use partial fractions as a tool. So the problems you would see in this homework aren't going to be brutal. They'll be pretty straightforward partial fraction problems. All right, so anyway, so to finish off this partial fraction decomposition, and if I get common denominator on the right-hand side, this fraction with a have to multiply by n plus 1 in the denominator and n plus 1 in the numerator. And then ditto on the second fraction. So the fraction with b in the numerator, it's missing the n minus 1 in the denominator for my common denominator here. So I multiply by n minus 1 down here, multiply by n minus 1 into the numerator. And then so once I set my numerators equal to each other, I get this expression. And then one of the shortcuts we learned was plugging in specific values for the variable to zero terms out. So in other words, if I plug negative 1 into n, I get a times 0. So if I plug negative 1 into the left-hand side, there is no n over here. So plugging in n equals negative 1, this stays 2. Plugging in n equals negative 1, this becomes 0. Plugging in n equals negative 1, I get negative 2b, and so b is negative 1. And then if I plug in n equals positive 1, again, on the left-hand side, there is no n expression, so that stays 2. Plugging in n equals positive 1 in the b side gives me 0 times b, and plugging n equals positive 1 here gives me 2a, and I find out that a is 1. Right? So coming back up to my expression that I decomposed, I'm going to have 1 over n minus 1 plus negative 1 over n plus 1. So I have 1 over n minus 1. I'm going to leave a little bit of space here. 1 over n minus 1 plus negative 1 over n plus 1. So our original series, 2 over n squared minus 1, is equal to that guy. Now, my series of 2 over n squared minus 1 is going to equal the series of that simpler form. Now remember, we're going from 2 to infinity here. So instead of writing out the original version like we did in the very beginning, we're going to write out this simpler form, this decomposed form. So now let's write these terms here. Let's write out the terms that come from 1 over n minus 1 plus negative 1 over n plus 1. So if I plug in n equals 2, I'm going to get 1 over, so 2 minus 1 is 1. And then plus, plugging in n equals 2, I get negative 1/3. So there's the first term, 1 plus negative 1/3. When I plug in n equals 3, I'm going to get 1 over 2 plus, and I'm going to get negative 1/4. And when I plug in n equals 4, I'm going to get 1 over 3 plus negative 1/5. I think you can kind of start to see the pattern here, right? So if this is 2, I jump and get 4. And then this is 3. This is 1 greater than the half. This is 3, and I jump 2 to get 5. I mean, you can see that pattern with n minus 1 and n plus 1 in the denominators here, right? So I would have, what, 1/4, negative 1/6, and then 1/5, negative 1/7, and I'm going to say plus dot, dot, dot. Okay, so with this telescoping series, I'm going to change colors here, and let's scratch out the things that cancel. Now, this is a different cancellation pattern than we saw in that very first example. Notice that this cancellation pattern is the following. So I'm looking in this first term, the last number is negative 1/3, and then I skip a term, and it cancels with the first. Then, when I look at the second term in my series, the last number skips and cancels with the first. So it's kind of hard to describe, and I'm using very, very loose language here. And then when I look at my third term in my series, right? So let me scribble this down, right? Here was n equals 2, here was n equals 3, here was n equals 4, here was n equals 5, n equals 6, right? So again, when I looked at the n equals 2 term, I had the last number, and then I skipped to n equals 4. That canceled with the first. Then when I looked at n equals 3 term, the last number, skipped and canceled in the n equals 5, the first number. Right? And then when I look at the n equals 4 term, that last cancels with the first 2 terms later. And then when I look at n equals 5, the last number is going to cancel with the first 2 terms later. And then when I look at n equals 6, that last number is going to cancel with the first of 2 terms later. And that cancellation pattern is going to continue forever and ever and ever. So what I'm going to end up with here is, after all this cancellation occurs, let me switch colors again, I'm getting the term 1 over 1 and the term 1/2 that survive the cancellation pattern. So all of this equals 1 and then plus 1/2. So we get 3/2 as the sum of that telescoping series. All right, and then I don't want to spend a whole lot of time doing partial fractions here. So just to illustrate, the things that will vary with these telescoping series is that cancellation pattern. So let's just take a look at one more example. And for me personally, right, what I always recommend is writing out as many terms as you need to see what that cancellation pattern is for that particular series. So, for example, let's suppose I had already done the partial fractions, right? And I ended up with, let's say, 1 over n, let's say, minus 1 over n plus 3. Let's say we had that, right? And n goes from 1 to infinity. So if I'm writing out the terms, right, I'm going to write out as many terms as I can, just like I mentioned. So I'm going to plug in n equals 1, and I'm going to get 1 minus 1/4. And then I'm going to plug in n equals 2. I'm going to get 1 minus 1/5. And I'm going to plug in n equals 3, get 1/3. Minus 1/6. So we have 1 minus 1/4 plus 1/2 minus 1/5 plus 1/3 minus 1/6 plus 1/4 minus 1/7 plus, let's see, this was n equals 1, 2, 3, 4. So if n equals 5, 1/5 minus 1/8, and then so on and so forth. Now, this might not be enough terms for me to see the cancellation pattern. So let me stop, see if I can see the pattern, and then if not, I will come back and finish the pattern. So let's see, here's my pattern, right? So what's happening? So looks like the negative 1/4 in my n equals 1 term is going to 1, 2, 3. So let's say here's 1, 2, 3, 4. So in the n equals 4 term, those cancel. So it's like I'm skipping 3 terms later. In the first term, the last number skips 1, 2, 3, cancels with the first and the next. And the third later, right? It cancels with the first, and the 3 skips away. So I'm going from 1 to 4 to see that cancellation pattern. And then at my n equals 2 term, the negative 1/5 is going to skip 1, 2, 3 away to the n equals 5 term and cancel with that first. And then at the n equals 3 term, the last number is going to skip 4, 5, to the n equals 6 term, and it's going to cancel there. And then in the n equals 4 term, am I doing this right? Let's see. So I had the last of the skip first, and then last skip first, and then last skip first, and then last skip first. Right? And then this last will skip first. So it looks like in this case, the things that survive are the 1, the 1/2, and the 1/3. So this becomes 1 plus 1/2 plus 1/3. And I guess I could get a common denominator there. Common denominator would be 6. So I'd get 6 plus 3 plus 2. So 11/6 would be the sum of that telescoping series. Okay, so let's suppose that, the instructions here, we're trying to be as rigorous as possible. And we're being told to, use the sequence of partial sums. Let's use the nth partial sum to prove that this series converges. So now that I've played with the series and I see the cancellation pattern, right, here's going to be my approach. So I'm going to write out, let me switch back to blue. So I wanted to zoom out here so we could just kind of keep referencing our cancellation. So my nth partial sum is going to be, right, so I'm going to write out the first term that we had, the 1 minus 1/4, and then I'm going to have the 1/2 minus the 1/5, right? And then I'm going to have the 1/3 minus the 1/6, right? And then I'm going to go ahead and just for me, I have to see everything kind of written out nicely. So plus, and then I'm going to go ahead and do the next one that we did there. What did we have? 1/5 and 1/8. Then I'm going to say plus dot dot dot. And then what I like to do is back up a couple terms. And what I mean by that is, this is the nth expression. 1 over n minus 1 over n plus 3 is the nth term. Right? So I'm going to back up to, let's say, I'm going to back up to the n minus second term. So I'm going to plug in n minus 2, then I'm going to plug in n minus 1, and then I'm going to plug in n, and I'm going to stop there. There's the sum of my first n terms. Right? So that's how I like to develop this. So if I plug in n minus 2, I'm going to have 1 over n minus 2, and then minus 1 over. So if I plug n minus 2 in here, I get n minus 2 plus 3 is n plus 1. And then I'm going to plug in the n minus 1 term, so I'm going to have 1 over n minus 1. I'm trying to squeeze all this into my digital paper. So here's n minus 1, and then n minus 1 plus 3 is n plus 2. And then my nth term. Oops, these are minuses. Let me come back and change that. I'm going to fix that with my digital eraser. This was a subtraction, and this was a subtraction. Okay, so here is my nth partial sum. Now, we already know the cancellation pattern, right? So I'm going to take out the gray. I'm going to kind of point out our cancellation pattern. Very loose terminology here, right? We were saying and within the n equals first term, I'm going to skip, right? 1, 2, 3, and then that cancels, right? And then we already know from our pattern, right, that if I look back up here, my 1/5 skip 3, and that cancels. I mean, I know that's going to cancel. Skip, and it cancels here, right? And then I know negative 1 6 will cancel out here somewhere, right? Okay, so what does that mean then when I get to the end of my series? So I'm going to look at this backwards. So let me come back up here with what we started with. The very first term we had the negative 1/4, right? And then we skipped 3 later and had the positive 1/4. And I'm going to look at this backwards. I'm going to say the first term of 1/4 canceled from 1, 2, 3, the last 3 before it. So when I look at my very final sum, the 1 over n will have canceled with the last number 3 prior. So this, I'm going to skip 1, 2, 3, and it would have canceled 3 prior. Again, let me point that out to you. Looking back up here with real numbers, the positive 1/4 here, I did 1, 2, 3 terms prior, was the last one. Right? You know, I would have a positive 1/5 in this term here. So the first term here canceled with skip, skip, 3 prior, last number. So again, first term here, skip, 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 3 prior, cancels. Right? First, so in my next to last term, this first term is going to cancel skip, 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 first term 3 prior. And ditto with this guy, right? This first term is going to skip, 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 cancel 3 prior. All right, now I'm going to think the other way, because my question here now is what's happening in these last 3 terms. What is the last number in these last 3 parenthetical terms going to do? Now, so I start to think back in the original direction. When I look at any given parenthesis, the last number cancels 1, 2, 3 terms later. So when I look at this term right here, this was my n minus 2 term, this was my n minus 1 term, this was my nth term. So when I look at my n minus 2 term, this last number in that parenthesis is going to skip, 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 cancel with the first one over here, which I don't have. I didn't go out to my n plus first term. I stopped at my nth term. So this won't cancel. And then this one also, right? The last, so if I look at the n minus 1 parenthetical expression, the last number there, negative 1 over n plus 2, I'm going to cancel with the first thing, first number, 3 parentheses later. So 1, 2, 3, and I'm not there. Right? So what's going to happen is the first 3 numbers in our series, 1, let me switch to red, that's what I've been using, 1, 1/2, and 1/3 survive, and negative 1 over n plus 1, negative 1 over n plus 2, and negative 1 over n plus 3 survive. So if I'm writing out the expression that represents the sum of the first n terms, what I have then is that S sub n is 1 plus 1/2 plus 1/3 minus 1 over n plus 1 minus 1 over n plus 2 and minus 1 over n plus 3. So this is the formula, if you will, for the sum of the first 10 terms. And then the infinite sum, right, which we typically just say S, is the limit of the nth partial sum as n goes to infinity. So if we just come back up here and look at this nth partial sum, I'm going to switch colors again. Let me switch to gray again. Right? So as n goes to infinity, 1 over infinity is going to go to 0, 1 over infinity is going to go to 0, and 1 over infinity is going to go to 0. So, yeah, we can write that this is equal to 1 plus 1/2 plus 1/3. I'll just say minus 0, minus 0, minus 0. So we're referencing that work up there. And then that was what we had originally when we saw that cancellation pattern. All right, so if we're just exploring to look for the cancellation pattern and give the sum, we don't have to go through this more rigorous approach of looking at the nth partial sum. But there are some textbooks, right, depending on the type of calculus course that I'm in, I may need to go through the justification using the sequence of partial sums, because in this section, that was how we began our conversation, was justifying that a infinite sum can converge by looking at the sequence of partial sums. Okay, so just want to do a quick summary of everything we've discussed in this video. This is a lengthy section, lengthy video. The very first thing we talked about was how can a sum of infinite terms be finite, right? Can it converge? And what we talked about was considering the sequence of partial sums. So we said if the sequence of partial sums has a limit that exists, then when I add them all together, that will converge. And again, we explored this concept by looking at, some tables of values. Right? So back in the very beginning of the video, we looked at 1 over n cubed. We added the first 2, 5, 10, 100, 500, and we saw this sequence of partial sums converging. And then, ditto in this example here, we saw that the sum grew and grew and grew, and so the sequence of partial sums diverged. Right? So that limit did not exist. So then that led us into the conversation about the test for divergence, or sometimes called the divergence test. And the divergence test says that if the numbers in the series, right, so if the sequence of numbers that we're adding in our series, those numbers don't go to 0, then the series will never converge, right? It'll always diverge. So again, our conversation here was, in this example, n over 3n minus 1 goes to 1/3. So ultimately, we're looking at 1/3 plus 1/3 plus 1/3 plus 1/3 forever and ever. So if the terms don't go to 0, then the divergence test says the series will diverge. Now, right after we discussed that, we wrote the test for divergence, where we said if the terms of the series don't go to 0, the series will diverge. And what we cautioned ourselves on was that there was a theorem in the textbook that says that if the terms do go to 0, we aren't guaranteed convergence. So we want to be really careful here. The converse of this theorem is not necessarily true. So if the terms don't go to 0, the series definitely diverges. But if the terms do go to 0, I am not guaranteed convergence. Right? And again, just to scroll back up to our data that we had here, here was an example of the terms going to 0. Where did that guy go? Here we go. Here was an example of my terms 1 over n go to 0, but the series of sequence of partial sums, right, the series diverged. So we always want to be careful with our test for divergence, and that we don't assume that if the terms go to 0, that means convergence. That is not true. If the terms go to 0, it might diverge, it might converge, but that if the terms don't go to 0, it definitely diverges. Now, all that being said, if the sum does converge, then the terms had to have gone to 0. So the only way that the series is ever going to converge is if the terms do go to 0. But the terms going to 0 do not guarantee convergence. So we talked about this again earlier in the video, that the terms have to go to 0 fast enough. So quote unquote fast enough. If the terms go to 0 fast enough, we will get convergence. If they don't go to 0 fast enough, we won't. And in a couple sections from now, we'll further define what does fast enough really mean. Right, and then we talked about a geometric series. We talked about the common ratio of the geometric series. We talked about in order for this geometric series to converge, that common ratio has to be less than 1. So we looked at a couple examples that we justified graphically, and we talked about where this geometric series converges or diverges. We developed the formula that gives us the sum of the n terms in the series, so our nth partial sum, like we've been talking about all along, and then when we took a limit as n goes to infinity, we saw that that became a over 1 minus r, right? That was my sum of my infinite series, a over 1 minus r right there, right? So as long as the series converges, as long as r is less than 1, then my geometric series has a sum of a over 1 minus r. And then there's us writing that summary. All right, and then the last thing that we've just looked at is the telescoping series. Lengthy video, all very important and foundational for the rest of this conversation in this chapter. I look forward to seeing you guys in the next video.